Welcome students, and in this video we are basically trying to look at first order differential equations. Yes, so as I have already explained, we generally are not going to study this in much details because solving this sort of equations we already know there are some techniques, integrating factors, and when the equation is exact, that sort of thing, right? We know how to solve those things, so it's not the primary concern here in this video. Essentially, what are first order equations, how does it look like? So the general solution, the general form will look like this. General form of a first order OD will look like how does it look like? Y prime equals to f of xy, right? Now if f of xy, let's say it is of the form axy plus b of x, right? Then let's call it 1. 1 is inhomogeneous. Inhomogeneous is when b is not 0. Linear equation, right? Linear equation, and it is very easy to solve. You just find out the integrating factor and you can solve it, right? Okay, now it may happen that f of xy may not be linear in y, so basically it can have y square, y cube, that sort of thing. Okay, so for example, let's just say that let me just put it this way. Let's say if I ask you to solve this equation, y prime plus ay, or forget about ay, let's just say this, so motivation, this is, let me put it this way, this is a motivation, motivation of what we are trying to do in this part. Motivation, see, let's just look at this. Y prime plus y equals to, let's say, x square. So this is a linear equation, right? Linear equation, and it is relatively easy to solve. No problem, you just find out integrating factor, it's done, right? Okay, now let's say if I change it to y prime plus y square equals to x square. Now change it to this equations. Now you see, you do realize that this equation is anyway not very easy, so this is comparatively difficult to solve. Okay, and you understand that I mean, you can make it more complicated by just adding, let's say, this sort of equation, e power y and all. So what happens is, although linear equations are very easy to solve, non-linear equations, although they are first order, they can be very, very complicated. Clear? Okay, so what do we do in such a cases? So what I am trying to say is this: in most of the cases, non-linear cases, solving the equation is not easy, right? Or it may be very, very difficult. Not easy means it may be very difficult. Okay, so what we do is, in those kind of cases, we try to find out whatever information we can get for a solution. Okay, and to do that, we look at something called a differential inequality. Okay, differential inequality. Okay, so what is this differential inequality? So let's say a function y of x is said to be a solution of the differential inequality y prime greater than f of xy. Okay, in this interval, let's say x naught plus a. Yes, if a y prime of x exists in this interval, Okay, so let's call this interval as I. In I and B, y prime of x should always be greater than f of x, y of x. So this should be satisfied for all x, right? For all x in I. Okay, then we call it a solution. So basically, if I change it to, let's say, less than equal, so y prime is less than f of x, then we will have this the sign changes, right? Okay, and if it is greater than equal, let's say, then also we just have the equality here. Okay, so we can just modify accordingly. So what is an example of such a thing? What is, where do we use something like this? See, the thing is, for example, yx equals to cot of x. Okay, so this you can see is a solution of y prime which is strictly less than minus y square. Okay, and it is in, what is the interval here? 0 and pi. Clear? So that's the interval. Now the thing is this, so you do understand what I'm trying to say. See, the idea is this: for most nonlinear equation, at least first order, here we are talking about first order. Okay, we may or may not be, it may or may not be possible to find an explicit solution, right? So you may not be able to solve that problem. Yes, and then what you do is, let's say you have this equation y prime equals to f of xy. Okay, you find two equations which is something like this: y1 is less than f of x y1, and you find a y2 such that y2 greater than f of x y2. Yes, and of course some initial conditions should be there, and you want your y to lie between, okay, y1 and y2. You understand? Something like this. So basically, you see, if you can find a y1 such that this happens, and if you can find a y2 such that this happens, you expect your y to lie between y1 and y2. So basically, you get an, you know, a quite nice cushion between two functions. You can sandwich your original solution, so you will get an idea of what your solution is doing essentially. Okay, so with this we are going to write down our first theorem here. So whether this sort of thing can or may work or not, let's see. So let f of xy, okay, be continuous in a domain D. Whatever the domain is, doesn't matter. I mean, wherever it is defined, let's just say. And y1 of x and y2 of x, clear, be the solutions of the differential inequality So these are called differential inequalities, right? y1 prime is less than equal f of xy1, okay, and y2 prime is greater than equal f of xy2, right, in whatever the interval where y1 and y2 are defined, the common interval. Then if y1 of x naught, okay, is less than y2 of x naught, okay, so essentially what I am doing is, I am saying that, let us put it this way. See, y1 is following some rule and y2 is following some rule, right? And so essentially I want to trap my y between y1 and y2. Okay, so basically I am saying that, let's say that y1 starts from, this is y1, okay, and x naught is 0, let's say x naught is 0. Okay, so wherever it is starting, y1 is below y2. So y2 maybe like this, let's just say this is y2, okay, and if y1 and y2 satisfies those two equations, then you know that y will maybe a solution like this, y will be in between y1 and y2. Clear? Okay. And what is the relation between y, y1, y2? See, y satisfies y prime equals to f, and y1 and y2 satisfies these two conditions. Okay. So if the initial conditions, initially they are below, y1 is below y2, then that will imply that y1 of x, right, is below y2 of x. Okay. See, this is the motivation. Okay, we want to go here, but for that we are starting with this theorem. Okay, we'll come into this, but we are starting with this theorem. So basically what we are saying is this: if you have two relations such that y1 prime is less than f and y2 prime is greater than f, and if y1 is below y2 all the time, okay, initially, then it is always below y1 is always below y2 for all time. Okay, so for all x in I. I hope this is clear. So what I am saying is, if y1 and y2 both satisfies the equation and y1 starts below y2, then y1 stays below y2 for all x. Clear? So what is the proof? Let's look at the proof. Okay, this is the proof. So let's say that this is not true. Yes. So let us assume that y1 of x is not equals to is not dominated by y2 of x for all x in I. What does it mean? It means that there is a x naught in I such that this is not true. Clear? Okay, then this set, so then the set A, let's just call it A, and how do we define it? It is the set of all those x in I such that y1 of x is greater than equal y2 of x. Okay, this set is non-empty. This is clear. Why? Because you see, if y1, so I am starting out with y1 below y2, right? If y1 stays below y2 for all x, we are done. So basically we are saying it does not. So basically there is a point x naught where y1 dominates y2 at least. Okay, at least dominates y2. So greater than equal y2, right? Okay. So if that is the case, then the set A is of course non-empty. Yes, right. So this is a non-empty set, and of course it is bounded below because the set is bounded below from x naught. Okay, see, x naught is the initial point. So this I will write it as x naught plus some A, let's say, open. Clear? Okay, so it is bounded below by x naught and it is non-empty. So basically what I can say is there is a GLB. So GLB of A exists, and let's call it a x star. Yeah, GLB is the greatest lower bound. Sorry, I made a spelling mistake. Greatest lower bound. Clear? Okay, so the GLB exists, yes, and is given by x star. And you also know that x naught. So what is the relation between x naught and x star? X naught is strictly less than x star. Why? Because you see, at the point x naught, y1 of x naught is strictly less than y2 of x naught. Clear? Okay, so x star has to be greater than x naught, right? Okay, so and what happens to y1 and y2 at the point x naught? Since it is GLB, y1 at the point x star equals to y2 at the point x star. It has to be, right, because y1 and y2 are continuous functions because of continuity. Okay, right. So if this is the case, what is happening is this. See, for H negative, okay, let's look at y1 x star plus H is dominated by y2 x star plus H, right? And hence y1 prime x star minus 0. So basically if I am approaching y1 prime from the left of x star, okay, that will be given by limit h tends to 0 y1 of x star plus h minus y1 of x star by h, right? So this is again dominated by limit h tends to 0 y2 of x star plus h minus y2 of x star by h. Okay, let me put it this way, by h. Okay, so why this greater than equals to sign? Let's just understand that. See, at x star y1 and y2 are basically same, so nothing happens here. Y1, see, for h negative, y1 of x star plus h is dominated by y2 of x naught plus h. See, for h negative, y1 of x star plus h is dominated by y2 of x star plus h, right? So, and since y1 and y2 are basically same at x star, y1 of x star plus h minus y1 of x star is dominated by y2 of x star plus h minus y2 of x star, right? And then I will divide it by h, right? Divide it by h, but this h is negative, so basically this h is negative, so this sign changes, okay, and that is why this is greater than equals to, clear? Okay, and y equals to, because I am taking the limit as h tends to 0, right? So that is why this equals to sign is there, because of the limit. This is equals to is because of the limit. Okay, so now what is it? This is nothing but y2 prime acting at x star minus 0, right? So you see, what is y1 prime at x star? It is nothing but f of x star y1 of x star, right? Okay, see, y1 prime is dominated by f of xy1, right? So let me put it this way, and y2 prime dominates f of xy2. So basically what does that means? F of x y2 of x star y2 of x star gets dominated by y2 prime of x star minus 0, and that is again dominated by y1 prime of x star minus 0, and y1 prime is dominated by f of x y1. So this is less than equal f of x star y1 of x star, right? Okay, so if this is the case, you see, you are saying that at the point x star, f of, and what is y2 at the point x star and y1 at the point x star, they are basically same. So this will imply that f of x star y, there is one mistake, there should be, this is strictly one, at least one should be strictly, so either this or this, let's just do this one, we need this. Why we need this? Because of to find a contradiction here. You see, if this is the case, okay, then what happens is y2 at the point x star is strictly less than f of x star. You see, y1 and y2 are basically same as x star, so this is y2 of x star, right? Y1 and y2 are basically same at x star, so basically I am just replacing it. So this strict inequality is required, and this is a contradiction. Okay, why strict inequality I am getting? Because this is our assumption. You see, I made a mistake here. At least you do realize that by making that mistake, you do realize that at least one of them has to be negative, strict. Either this or this. Even if this is strict also, then also the same sort of thing will work, right? Okay, so you need at least one strict inequality. Okay, so once that is there, then you have a contradiction. Therefore, the set A is empty, right? And what does that mean? It means that y1 of x, so if it starts below, okay, the initial data, whatever the initial data, let's say x star, if it starts at x star, y1 starts below y2 at x star, it stays below, right, for all x in let's say I, and what is I? I is nothing but x star, sorry, x naught and x naught plus some a. Yeah, I don't care what a is, some a. Clear? Okay, so that is there. Now you see what I am going to do is I am going to write down a corollary of this theorem, and this is the corollary which we want. You see, I told you, right, we want to sandwich the solution between those two inequalities. So how do I do it? So let's say that let f of xy is continuous in some domain D, continuous in a domain D, whatever the domain is, domain D. So let's just assume that there is a domain D where all of this is continuous. Okay. Now further assume that a yx is a solution of y prime equals to f of xy. Okay, in I, and what is I? X naught plus a. Clear? And B. So this is the first condition. You need y. I am starting with y, which is the solution of this equation, and y1 of x and y2 of x solves the inequalities, the differential inequalities, that is inequalities. What is the inequalities? F of xy1 greater than y1 prime and y2 prime greater than f of xy2 in x naught plus a. Clear? So this is the second condition. The third condition, we need another condition. Why we need another condition? Because in the earlier cases, if you remember, we know this data that initially what is happening to the solution. So basically we say that initially if it is below, it stays below. So we need that sort of initial condition. So we need to know what does y1 and y2 does initially. So basically see, y1 at the point x naught must be dominated by y at the point x naught less than equals to, which is dominated by y2 at the point x naught. Let's just assume this. Okay, then we can say that as earlier, if it is dominated at the initial data, it will be dominated everywhere. So basically y1 of x gets dominated by y of x gets dominated by y2 of x. Clear? This holds for all x in x naught plus a. Okay, why I am writing open x naught? Because at the closed x naught we are already given what does y1 and y2 does. Okay, so what is the proof? Let's look at the proof. Okay, another small remark I have to put it here. You see why here this inequality is strict. Okay, it is not less than equals to but equals to. So he is saying that although at initial data they may be equal, but they have to part ways. Okay, so they have to be strict once they go out. And why is this happening? Because of this strict inequality. You see here both the inequality which we wrote are strict. Okay, right. So let's look at the proof. So we'll just prove the one part. Let's say we prove this part, the other part is exactly the same, it doesn't matter. Okay, it's the same thing. So let's say that if y naught, which I am defining it as y at the point x naught, is less than y2 at the point x naught. Yes, if something like this happens, then you see y of x should always be less than y2 at the point x, right? This is always true. Why? By the previous theorem. Yes, so essentially you can see that the previous theorem, what does it say? It says that one strict inequality and one less than equals to is fine, and if you are starting out with some difference, then the difference persists everywhere. Okay, strict difference. Here also you see the both are strict inequalities, right? So that is satisfied. And now the thing is this, one is equals to and one is strict, right? And you see at initial data, so they are essentially what they are doing is this is strict initial data. This is what our assumption is, and then the solution stays strictly unequal, right? Okay, so this is always there. Now let's say that they are same, then what happens? Okay, so let's assume y naught, okay, is equals to y2 at the point x naught. Let's just assume that. Okay, so then define, what I will do is this, then define z of x, which is y2 of x minus y of x. Clear? If we do that, therefore z prime of x is what? It is y2 prime of x minus y of x, right? That's what we are going to get, and this is greater than equal f of x y2 at the point x minus f of x naught y at the point x naught, right? This is what we are going to get evaluated at the point x naught. That is, sorry, I just, okay. So this is true because you see we assume that y2 prime is strictly greater than f of x y2. So this is true for all x. So for x naught also it is true. Okay, and see, this is nothing but 0 because I have assumed that y2 at the point x naught is y at the point x naught. Okay, so this is true, 0. So I have z at the point x naught is strictly greater than 0. That is what I am getting. So that will imply that zx is increasing in the right of x naught, in the right of x naught, right? In the right of x naught. So basically x naught is the starting point, right? So it is increasing in a small neighborhood, let's say small neighborhood. So what is the neighborhood? So that is in this neighborhood, let's say at x naught plus some delta. Let's just assume that for some delta greater than 0, for some delta positive, small enough, right? So essentially what I am trying to say is this is z prime x naught is positive, strictly positive. So what does that mean? It means that, and it starts from x naught, right? So it means that it has to increase, at least for some time it has to increase, right? For some delta. So that is there. Okay. So therefore, if z is increasing, it means that y at the point x naught plus delta here is strictly less than y2 at the point x naught plus delta. It is increasing, right, at that interval. So this is true, right? Of course, I mean, you can write it by delta by 2. So let me, without loss of generality, let us write it as a closed interval x naught plus delta. Of course you can do it, otherwise you take delta by 2, doesn't matter. So we can do this. Okay, now you see you have your new initial condition, which is x naught plus delta. So you look at the functions, these functions at x naught plus delta, they are, if you think of it, it starts from there. Okay, so y1, y2 starts from x naught plus delta. So for all x after x naught plus delta, y of x must always be less than y2 of x for all x greater than equal x naught plus delta. This will imply this. This is from the previous theorem. Right? Okay. So you see what is happening is this. Therefore, choosing delta greater than 0 sufficiently small, one has y of x is strictly y2 of x, okay, for all x between x naught and x naught plus a, right? x naught and x naught plus m. Clear? So this is true. Now you do it the other part also, exactly the same sort of thing works. So you please do this part and then we are done. Clear? Okay, now let us look at one example. So let me give you an example of how to use this fact example. So let's say that consider the initial value problem. What is the initial value problem? Y prime equals to y square plus x square. Okay, y at the point 0 is 1 and the interval I, in the interval I, which I am choosing it to be close 0, 1 open. Clear? And in this interval I want to find out that if I can without solving, like, of course I can solve this, but the thing is, without solving this equation, can we find a lower bound and an upper bound? So essentially in this part we are basically looking for a lower bound and upper bound of a solution, and you can actually get it using this theorem. Okay, right. So how to get something like this? See, for that you have to produce a y1 and y2 which does this, right? y1 prime has to be dominated by f of xy1 and y2 prime must dominate f of xy2. And what is f of xy? F of xy is given here. You see, f of xy here is nothing but x square plus y square. Okay, you have to find one y1 which gets dominated by f and y2 which dominates f, right? So then you have this equation along with the initial data, of course. Okay, so how do you find such a thing? So let's assume maybe let y1 of x, okay, is 1 plus x cube by 3, okay, and y1 at the point 0 in this case is 1, okay. So which is similar, you see, y at the point 0 and y1 at the point 0 is 1. You see, both seem equals to, if the equality holds, it works. Huh? So you see, y1 of x, if I am choosing it to be 1 plus x cube by 3, what happens to y1 prime of x? Let's just calculate this. It is nothing but x square, which dominates x square plus 1 plus x cube by 3 square, which gets dominated by this, right? Okay, and what is this? This is nothing but x square plus y1 square, right? So you see, I have a y1 such that y1 prime x is strictly less than x square plus y1 square x, which is nothing but f of x y1 of x, right? Now similarly if you choose y2 of x, okay, to be tan of x plus pi by 4, right? If we choose this, and you see, what is y2 at the point 0? Of course you can understand that x equals to 0 is tan pi by 4, which is nothing but 1. Okay, therefore y2 prime of x is equals to, what do you get? It is the derivative, it is sec square of x plus pi by 4, right, which is nothing but 1 plus tan square of x square pi by 4. Clear? Right. Now this is dominated by 1 plus, this is dominated by, see, tan square of x plus pi by 4 is y2 square, right? And so this is y2 square of x plus x square. Okay, see, x is always between 0 and 1. Okay, so 1 dominates x square. I can write it like this. Therefore you have that 1 plus x cube by 3 here is dominated by yx. Why? Because of this theorem. You see, in this case yx dominates y1 and dominated by y2, and it will be dominated by tan of x plus pi by 4. Okay, and this holds for all x between 0 and not till 1 but pi by 4, because you see I have this tan, right? So up till tan 90 it will hold. So essentially it is x lies between 0 and pi by 4. So in this interval you can actually get that there is this upper bound and lower bound. Hence one finds an appropriate appropriate upper and lower bound. Upper and lower bound. Lower bound. An important thing is without solving the equation, right? Without solving the equation. Clear? Is this clear? Okay. Right. So with this, I am going to end this video.